I don't know, I forget what my actual title of this talk is actually at this point, but we've switched it up a little bit. And Lars covered some of the magnetar and unusual supernova. And I wanted to finish up some of what I was saying last time about supernova spectra and finish that discussion of how to understand supernova spectra. Lars said I would show a spectrum of a type 2 and other things, so I put up this plot. So here's your nice type 2 supernova and your other type of supernova. This is a plot I made in I don't know, I just made this in graduate school, and it's floated around, I think, since. I just saw it appeared in a book that's come out now. There's a book now on supernova by Branch and Wheeler that's just out. You can get it on Amazon, which is kind of nice. A thick book that covers a lot of phenomenology of all types of supernova.
Less than 5,000?
What's that?
Less than 5,000.
Less than 5,000?
Dollars.
No. This one, no. Oh, there's a supernova handbook, but there's also a supernova text, which is $100. That's a little bit more affordable. So, but then there's a supernova handbook that covers, I don't know how many volumes that is. So, but anyways, these are the different types color-coded by their different elements. And I misspelled sulfur here, and it's been bugging me for about 15 years, but I don't know how to change it. So. Anyways, you see these interesting things. I said this last time, the spectra are sort of, quasi-black bodies with these broad absorption features. Actually, they're kind of P Cygni profiles with absorption and emission. You can see it especially here in this hydrogen. There's a little bit of absorption and a lot of emission. In other cases, there's more or less absorption or emission. And what I was trying to get at last time was to tell you a little bit about how radiation transport works in supernova. And I'll kind of finish that up and tell you how you can understand spectra and calculate some of your own spectra as well. What Ren was saying, I think, if you're like me, the only way you really learn anything is by doing something. I mean, it's good to listen, but you don't really absorb it until you do something. So I put up some notes. They're kind of worksheets that I had that can guide you through some of this stuff that may be useful. Actually, I can put up, if you go to this website, just the GitHub, my GitHub, and I called it Supernova Lines, you'll find there some stuff relevant to the discussions we've been having. Maybe we can send that out as well. So on that website, I put up, I showed you last time some information on supernova spectral lines and how to identify lines. So there's some Python code there that you can use to identify lines. And then there's two sort of kind of worksheets for you to work out yourself some of the physics that we've been talking about. So one about modeling light curves. So we heard about this from Udi, and I may go into a little bit of this as well. That kind of guides you through starting with a general equation for energy conservation, all the way through how to derive your own analytic light curve and write a little code to calculate it. And it'll take you step by step through that. And by the end, you should be able to make your own light curves and fit it to data or make predictions from your models. And it shouldn't take you that long. And then as well, there's a little worksheet about modeling supernova spectra, which I'll talk a little bit more about here as well. This guides you through the physics essential to model optical supernova spectra. And again, write a little code to do so. And then I actually have a little code here if you're interested in looking at it, a little Python code to generate a supernova spectral line that you can play with and understand kind of firsthand what's going on. And you can write this yourself. It's only maybe about 40 lines, 30 lines of code. Actually, most of that is comments and stuff. So what we're saying, if people are interested, we could get together sort of after the program today and maybe go through some of these problems or at least discuss some of the physics that's going on. Okay? And so, what I wanted to get to today is a little more following up on what I said about how spectral lines are formed in supernova ejecta, or actually this applies to a broad range of transients. It could be supernova, it could be kilonova, tidal disruption events, or any other thing where you have some outflow. And you have this generic P Cygni profile where you have blue shifted absorption and red shifted emission, but you can get a wide range of other things. And there's a lot of information there in terms of the kinematics of what's going on in the composition, and as we'll talk about the geometry as well. So maybe if I could get the screen to go up, I'll finish up some of the discussion that we did last time. And then I'll tell you how it plays out in terms of opacity in general and light curves of supernova and kilonova. Okay? We've heard opacity come up a bunch of times in this winter school, and usually it's just some number that we throw in there. But for lots of supernova, like type 1a supernova, and kilonova in particular, it's the lines that are driving the opacity. So understanding what makes the supernova distinctive is really understanding line transport. So let me go through just a very quick review of what I said in my last talk, which you might have forgotten because it's already been 2 days, but it was basically describing sort of what happens in a supernova atmosphere, where you have some photosphere or something. And what I said is if you emit some photon from, say, the photosphere of that supernova, as it moves through, it's continually Doppler shifting with respect to the co-moving frame. And so if I looked at the opacity, and let's say we were considering the case where we had some optically thick photosphere and maybe a single line of opacity outside of it. What we showed was that as this photon moves through this medium that has some velocity gradient, not only does it move it in space, but it moves to the red in wavelength as well. And in fact, we said for homologous expansion, we found the relationship between the movement and the wavelength shift. The change in wavelength in the co-moving frame, that is relative to where you sit here, was just related to its wavelength times the distance traveled over ct, since the distance traveled here over t is a velocity. This is just a standard Doppler shift formula that holds for homologous expansion. So there's sort of a one-to-one correspondence between the distance you go in space and the distance you move in velocity. Okay? And then what we said is as you go through, eventually you may run into one of these lines. That is, you'll come into resonance with one of those lines at some point here. And then there'll be some region of space where you feel that opacity of the line. Feel nothing until you hit the line itself, right?
This is somewhat unusual, but you can just ignore it and continue.
What's that? This. Can I take a seat there and relax? I get him. Okay. So as you go through, yes. Well, we needed a chair there. Yeah. So as you go through here, you find some region of resonance, and we said that region is quite small because the size here is just of order the thermal velocity times time. The thermal velocity sets the intrinsic width of that line. That's much less than the size of the supernova ejecta itself. So photons interact with lines at basically a single point in the atmosphere. Okay? So that was what we talked about, and then we said, well, what's the probability that a photon kind of makes its way through this line and comes out the other side without feeling anything, as opposed to, say, scattering and going in some other direction? That is the line a strong one or a weak one, which is what you want to know if you're analyzing one of those supernova spectra I showed before. Why are some of these lines strong, like calcium or silicon, and why are other ones not visible? And we calculated that, well, just by integrating the opacity over this line, and we came up with this Sobolev optical depth, which we just said was proportional to some statistical weight of the lower level of the transition, oscillator strength, the wavelength of the line, and then some Boltzmann factor. Okay. With some other factors, but this is sort of the estimator for which lines are strong and which ones are weak. And so that's what is linked to on that on that page is the code that will basically give you all the lines and sort them by their relative strength in this way, so you can identify which lines you expect to be strong. Okay. All right. So that was just basically telling you how photons interact in a supernova atmosphere. What we want to really do is then generate a spectrum and say how this gives us what we see in the line features that we see. And the assumption that we made here that this region is very small where the interaction happens means that we can actually easily write down what an observer sees. So that's ultimately what we're interested in, is what an observer would see looking at this supernova environment. You have some, say, specific intensity ray coming here towards the observer. And actually, we're going to want to integrate those up over the entire supernova ejecta to construct what the observer would actually see. And so let's say we have a line here, a ray here that comes into resonance some point right here, just like we've seen that. Now, what we'll get to is that, of course, I drew some photon here that came into resonance with a line over here. But of course, there'll be this photosphere is emitting photons at all different wavelengths, and they'll all go in different directions, come into resonance at different points here. If I, emit a photon at this wavelength closer to the line, it'll come into resonance nearby. If I emit one farther away, it may not even come into resonance at all until it's already left the supernova ejecta. So what happens to the observer when they see something like this? And we have some optical depth here. Well, it's simple enough to write down the solution here, since we have the interaction happening at a single point in the supernova ejecta, and we know the optical depth going through that point. It's just a standard result for the intensity that's seen from this ray, and then we'll start adding up all the different rays. And that's your standard result for some constant medium. We can assume that the properties here are constant, and so the intensity the observer sees is just the intensity from the photosphere suppressed by an optical depth that's given by this quantity, which again is a local quantity. It just depends upon the properties here. I should sort of put in a density here as well, a density at this point in space. But this line also emits radiation, so there's another term here for the emission from that line. All right, which was related to the source function of the line. So this is a source function. And in those notes that I have there, I'll give you various ways that you can estimate it. But basically, in LTE, that source function would basically just be the Planck function at whatever temperature you have in this resonance region here. Okay. All right. So it's a standard thing you might be used for line formation. You emit here some black body from the photosphere. If this line is very optically thin, basically tau goes to 0. You basically just see the intensity of the photosphere. If this line is very optically thick in that region, you basically see the source function of that line. That is, you see the black body at this temperature. And since this temperature usually declines with radius, if this is very optically thick, you'll see this in absorption relative to the photosphere, right? Of course, the observer is going to see radiation coming throughout the atmosphere, here, here, and here. And so if I take some beam here that look like that, well, here there's no backlit source from the photosphere, so the intensity you see in this case is just going to be source function, just the emission from the line itself, okay, without any attenuation of the background photosphere. Does that make sense? All right. So let's put it all together and actually write down the calculation to model the spectra. So the idea here is that if I take I'm going to draw this picture a lot. If I take my atmosphere here and I have say some emission going through this point. Let's put the observer right here looking at this supernova cloud, and we'll define this axis as the z-axis, and by convention it's usually defined going z is increasing away from the observer. Now if the observer sees light coming from this point here, what wavelength is the observer going to see that emission? So this is emission from some line at that point. What wavelength will it be observed by the observer? Let's say it has some rest wavelength, lambda naught. Right? So it's going to be Doppler shifted relative to the observer. The velocity here at this point is moving radially outward. In homologous expansion, it's just r over t. But the line of sight velocity, that is the velocity of this point in the direction of the observer along the z direction, is going to be r over t cosine theta, right, where this is the angle between the z direction and this point here. Right? So the observed wavelength of some emission from a line right here is actually going to be Doppler shifted by r cos theta over t divided by c for the Doppler shift formula. And of course, r cosine theta in these typical coordinates is really just z, right? This is a certain value of z. So this equals 1 plus z over ct. Okay? So in this coordinate system, the line emission from this point z, I can define this line going through here, z equals 0. Then this emission is observed. Well, I've defined here z going in this direction. So this is actually z.
The second equation is fine with the first one. Theta is what you drew.
Yes, I want it to go to a shorter wavelength, right? But z, remember, z is increasing this way. So this point here.
Okay in the second equation. Yeah, with the z it's fine. Upstairs it's okay.
Upstairs, okay. I see what you're saying. I see what you're saying. Yes. You would want a minus sign unless I define my theta in a different way. If I define the theta going the other way. Right. Okay. Yes.
have Z point to the right and then it would all listen.
The convention is to Z go this way, so that Z, yeah. In any case, Z goes this way. So this point here, Doppler shifts to this point. What about a mission from, say, right here, along the same axis? What wavelength does that map to the observer? Thoughts? Same. So it's at a different radial point, but the angle is different, and so the r cosine theta is the same. So the point is, and this is maybe the main takeaway from all this, all these points along this z-plane all map to the same observer velocity, same observer wavelength, right? That is this plane that I've drawn here, this line of constant z, is a line of constant, you might call it a constant directional velocity surface. Okay, and so in homologous expansion, all the material on this plane is moving towards the observer at the same velocity. Even though this stuff is moving faster, it's moving at a different angle. And what that means is all of the material on this plane maps to the same wavelength for the observer. Okay? So we can see how that works. Right. If I draw my wavelength down here, this point right in the center will be the rest, all the material on this plane will map to a certain wavelength on there. So when you observe a supernova at a certain wavelength, what you're really observing is emission sliced through the ejected cloud, okay, in a plane. And that lets us sort of decompose, in this sense, what we see. If we look at a different wavelength, it maps to a different point in space. Map here, okay? Now this is particular to homologous expansion. If you have a other sort of outflow like a wind, you'll have to calculate what those constant directional velocity surfaces are. If it's a constant velocity wind, you'll find that there'll be cones, and so each wavelength will be telling you about emission happening along some cone slicing through there. But this lets us really diagnose what's happening in the supernova atmosphere. All right, and so we can understand this P Cygni profile in some detail, and then eventually you can construct one on your own. So let me do it again. So here's the observer. All right, here's my wavelength dimension. And here's my z equals 0 plane, so this will correspond to lambda naught. And of course, the photosphere is emitting rays of intensity this way towards the observer, right? So if I take a plane out here and cut through, all I'm going to see, since this is cutting through outside the atmosphere, I'm just going to see the intensity from the photosphere coming through without any attenuation or extra emission from the line itself. So out here I'll just have the continuum, the luminosity of the photosphere. what happens if I look at a wavelength corresponding to, say, this slice? What am I going to see? Well, I'll see line emission throughout this plane here. Most of the line is actually in front of the photosphere, so it's obscuring it. And so I'll have absorption of the photosphere light. I'll have some emission too in this region and from these outside regions too, but that will usually be small compared to the absorption I get. But since the densities are out here are rather low compared to the central regions, I might just get a little bit of absorption. That is the optical depth. The Sobolev optical depth may be small out there, right? So basically I'll have this equation here, right? I'll have the photosphere attenuated by the Sobolev optical depth, but I'll be integrating it across this plane here that's cutting through this, in this case, a sphere. Right. So I'll see some absorption going through. Right. Not absorption from one place in the atmosphere, but integrated across this plane. If I take another slice through that maps directly to some other wavelength in the spectrum, here again I'll have absorption of the photosphere throughout this region. And since I'm even deeper in the atmosphere now where the densities are higher, the line optical depths are higher, I'll generally get even deeper absorption. Although it'll depend, I'll also have emission throughout this region here. So how much absorption to emission will depend upon what I choose for my source function, how that is. But usually I'll get even more absorption, and usually that will be deepest for a line that cuts right next to the photosphere, okay? Because there I'm cutting through the densest part of the atmosphere. So I'll get sort of some minimum happening here. Right. That corresponds to, again, the minimum velocity corresponds to basically absorption across this plane. All right. And then I can keep going with this game of taking some other slices here and seeing what I get. Now I get emission, right, from these outer regions that don't obscure the photosphere. I have resonant points inside the photosphere, but those, of course, are going to be blocked by this high opacity inner region. And so at this point, I'm going to have mostly emission dominating because I don't have on this slice any material that's obscuring the photosphere. So this is going to start to turn around and go into emission. And then this slice here, which is in back of the photosphere, again, is going to give me all emission without any obscuration. I can basically get. And then out here again, my wavelength maps to something outside the atmosphere. So there's my P Cygni line profile. The general intuition that you had about it, that, well, stuff coming towards me blocks the photosphere and gives me some blue shifted absorption, while stuff moving away emits and gives me some emission is right, but the detailed picture is to integrate along these lines here, okay?
You also get emission from the unblocked areas.
In which regions?
In the area where you integrated.
This part back here?
Between the observer and the photosphere. But
Yes.
the areas which are beyond the size of the photosphere that are emitting.
These parts here or out here?
Yes, here, but a bit more.
Oh, right here. Sort of here.
Or
Yeah.
longer.
Yeah. So when you're looking at, say, this wavelength here, you know, some parts of the atmosphere are absorbing the photosphere, so you get some attenuation here, and then you get some excess emission out here. And it's the sum of those that matter. So we're not just seeing pure absorption, we're seeing a sum of absorption, in this region and excess emission there. And how deep that makes the line, or whether the line's an absorption or emission, will depend upon doing this integration over that plane. Yeah?
The flux that we see at peak wavelength, that would not necessarily be emitted at the center of our coordinate system. It should probably be emitted at the photosphere.
Well, typically, you're saying right in front of the photosphere, or this is plot's getting.
It would be emitted at that radius. So I'm having a hard time understanding why it would be.
The question is, where is zero velocity in the wavelength?
So, yeah, let me draw it once more to make it clear. So, again, zero velocity is going to be this plane, well, this plane cutting right through the middle. I didn't draw it very well, but this is cutting right through the middle of the system. Okay? Yeah, and that maps exactly to the rest wavelength of the line, right? Because this is material that's all moving tangential to the observer, right? So it has no velocity along the line of sight. The z is 0. This corresponds to z equals 0. And so that corresponds to the rest wavelength of the line itself. And here you only get, you get emission from all these regions here. And so you generally get a strong emission here that will generally peak around here. But okay, and then out here you'll start to get absorption. Okay. So, schematic picture, and then I'll show you how to do it in more detail. Okay. So that's the picture, and it isn't too hard to try to make that more mathematically precise and do an integration. Any other questions before I? Yeah.
The minima is was update to the photosphere. Shouldn't it be exactly when it touches the photosphere instead of?
Yeah, so where does the minimum form? Again, there's not a hard and fast rule there. You need to do the calculation. And generally, a line that's, this plane that cuts right in front of the photosphere maps something close to the minimum, because there you're integrating over this plane that's in the densest region of the atmosphere, right? And so you probably get the strongest absorption here.
Yes, that depends on tau.
But it depends on how your tau varies and how your
Tau is
geometry
big.
varies.
Then you're already absorbing all of the
Yeah.
photosphere while you're to the right of it, so you
Right.
don't gain anything by going
Exactly.
to the left.
So I'll show you that in a second. Right, if tau is equally strong out here, or if it's even stronger out here, then you may even get more absorption out here. Okay? I'll show you some examples of that through the video. But you can get qualitatively the right picture, so we can have some fun with this. Spherical geometry is one thing, but a lot of times we may have a model with some, more interesting geometry. We may wonder what the what the diagnostics of that are. So let's say I had a supernova explosion or something that looked like this, or maybe it's a kilonova that had some disk-like geometry and so on. And I observed it over here. So what kind of signatures do I expect to see for this kind of geometry? Any thoughts?
What do you assume about the velocity?
Velocity is still homologous here.
You wouldn't
Right.
have the emission peak.
Why wouldn't I have an emission peak?
Because that's what was.
Yeah, so if I draw this line here again, which again maps to the rest wavelength, this is the z equals 0 surface, you're right. I have no material here to emit, right? Whereas if I draw this peak here that's blue shifted, I'll have some region that's absorbing the photosphere along with some emission as well, which I'll have to integrate out. But yeah, eventually I'll get something that looks like this. Here I'll get some absorption. I might go into some emission, but you're right. Here I'll lack my emission, so we'll get a dip back down to the continuum level. And now out here, again, I'm getting emission. Or I could draw this correctly. All right, so I'll get sort of this double humped profile, which we see sometimes as well, which would be an indicator. I'll show you some examples of this in data. Here I might get a double peak here along with my absorption, which is a direct indication of the geometry in the viewing angle. Okay. And so for almost any geometry you think about, you can just play the game of drawing these surfaces and calculating what you see. I'll do one more here that is often of relevance. Let's say I have some sort of photosphere, but my line emitting region is actually some thin shell. And my projecta is some thin shell above that, right? What would be sort of the diagnostic of this? Expect to see here. Thoughts? The game is the same. Each point here maps to some point. So out here, which is say the outer velocity of my shell, I'm going to get some absorption. But that's going to cut off somewhere near the inner velocity of my shell, actually probably somewhere a little shorter than that. And then for all other wavelengths, there's no material interior to obscure the photosphere, but there is material emitting, and actually you can do this analytically. If you take slices of a shell with a plane, you'll get sort of constant volumes here. So you'll get some very long emission feature here that's flat topped. Okay? Maybe something along those lines, right? And we see that as well.
Here, for example, at the beginning, you have approximately as much emission as at the end, when you have both absorption and emission.
Yeah, so let's see here. This is sort of just the raw photosphere emission. I get a dip of that, and then I get some excess emission here from these regions of the shell. And then this will cut off back and go back to the level here. So what exactly was your question?
At the time when you have absorption, you also have emission from these areas.
Oh, you're right. Yes.
And that's about the same amount that you have at laser times, right? Maybe
Yes.
you
I'll have some. You're right. I'll have some emission coming from this region as well. I mean, there's actually emission all throughout here. There's emission in here too. So it's just a question of which wins, whether the absorption from here is stronger than the emission here. So that depends upon the source function of this shell. If I made this shell, say, very hot compared to the photosphere, then I could get emission at all wavelengths. But if this is, say, a cold shell, so the emission is not very strong, the absorption will beat the emission. Right? This is this expression here, right? If this source function is small compared to the intensity of the photosphere. Okay, other questions? Yeah. Because this is, again, you'd have to do the geometry, and it's just a simple but fun exercise. If I take a slice through this shell at any point along here, I actually get constant. I'll get a constant contribution as I go through. Okay. So
the photosphere inside, does that produce anything, any emission?
yeah, it's still producing all the emission coming through, but I have some excess from the shell. Okay. Yeah, there's some background continuum, and then there's some excess above it due to the shell. All right. So you can do that all day. Everything I've talked about here is in the what you call the photospheric phase. That is, we've assumed we've had sort of some optically thick continuum source here. Of course, if we go late enough, we get into a nebular phase where that photosphere goes away, and then we can play the same game, but we'll just get, a line emitting region without any photosphere to absorb. So we won't see any absorption features, but we'll see emission features that we can calculate in the same way, right? If I had some ball sphere here at late times, now it's optically thin. There's no photosphere. But again, I can take slices. This will be the rest wavelength. That'll give me the most emission generally because I'll have the biggest slice out at the edge. The slice through the shell gives me something smaller. So I'll get some sort of emission feature that looks like that, right, in the late phase. No more absorption, but pure emission. All right. And again, there's strong information about the geometry of the system here as well. Again, if I had some, say, jet explosion, maybe I exploded nickel along some jet here and left oxygen out here, right? And I were to look at this at some late phase, I could draw the same sort of picture here where I'll get here no oxygen emission along the 0 point, maybe some double peak structure like that. All right, and then of course you can play this game of changing the viewing angle and calculate what's going on. All right. What's that? And then if you looked at the nickel here, yeah, you would see something different, right? So this would be the oxygen line. The nickel line would be mostly narrowly, maybe it would be, the inverse of that as well, right? So you can diagnose things, all right? So you can play this game sort of schematically of what's going on. If I can get the board down, I'll show you some actual examples and other things going as well. Well, maybe I can show you on the slides here. So here's one example of what I just showed you. This is from a type 1c supernova. Right. Actually, two type 1c supernovas that were looked at late times from different viewing angles. In one case, you saw sort of a double peaked emission in this type 1c supernova. In this other type 1c supernova, this was a broadline supernova associated with a gamma ray burst. You saw a single peak as well, right? And so one interpretation of these different line profiles is this geometrical distribution, which I just sketched out before. This is at late time, so we're not worrying about a photosphere. From this viewing angle, you're seeing slices through here, creating sort of the double peak, the lack of emission along here. Whereas from this viewing angle, you're seeing slices going this way. All right? And so it was observations like this that led Mansali and others to claim that we were seeing in this supernova evidence for a jet-like explosion. That is a distribution, at least, of oxygen. This is an oxygen line that was lacking material in these planes. These are two supernovas, so they're trying to build sort of a unified picture of these events. All right? And the fits here, you can do it yourself if you have your own model now, or you can make your toy model. You can construct these line profiles in a quantitative way and compare to data. I'll go through the equations again in a second for that. Here's another example from type 1a supernova from Maeda et al., where they're looking at, again, nebular phase spectra. And in this case, we have two lines, one from iron 2, another from nickel 2, in two different events. And you see, in this event, the peaks seem to be shifted from their rest wavelength to the red. In this case, they seem to be shifted to the blue. And the interpretation there was that you had a geometry that in the supernova where the nickel distribution was shifted from the center. And in some cases, you were looking at it coming towards you, and in other cases, you were looking at it coming away from you. Okay? There's other interesting examples in 87A and other things where you see interesting line profiles that can all be analyzed in this way. So the numerical calculation is straightforward, which is what we just laid out to calculate the luminosity at any wavelength. It's really just an integral over one of these planes that cuts through whatever geometry you have. So for some particular wavelength that you observe, it maps to some z-plane, and the luminosity you see is an integration over x and y, the dimensions perpendicular to that plane of this intensity. And the intensity you see we've now derived is either, depending on where you are, if you're in front of the photosphere, you have attenuation of the photosphere and emission. If you're to the side of the photosphere, you just have emission. And if you're, say, behind the photosphere, in the photosphere, you just see the photosphere intensity itself. And so that's a pretty straightforward integration to do, and that's what this worksheet that I have will guide you through, and the code will show you an example of that. And now you basically have all the pieces to construct your own spectra of whatever model you want, or to fit any observations you want. There's rules for how to calculate what this optical depth is, given some density and temperature and composition. And then there's some rule to calculate the line profile, given the distribution and geometry of the spectrum. We've done it for one line, but you can do it for many lines, and basically construct your whole spectrum. Yeah?
So do the spectra of type 1a supernovae show enough symmetry to distinguish between a single and a double J-like scenario?
It's tough to say. So in this case, this is one of the more interesting diagnoses of asymmetry, where you see these shifted lines here, which was interpreted as some kind of bulk offset of the iron group distribution. And how that maps to the right explosion mechanism is debated. In this paper in particular, they argued for one of these Chandrasekhar mass kind of off-center detonation. So I talked about that a little bit the first day. You take a Chandrasekhar mass supernova, you ignite it off-center, you have a bubble rise in one direction, wrap around and explode. And given this sort of bipolar expansion, you tend to get iron group elements produced primarily on one side versus the other. And so that kind of model, at least qualitatively, fits this. Now, if you wanted to quantitatively see that, you would take your explosion model that you made and generate these line profiles in the way that I described and see if you can actually get something that matches this. There's another example of type 1As where they see in some of these line profiles sort of double peaks, at least in one or two events. And there's a paper claiming that may be some indication of a collision scenario where you had two white dwarfs colliding sort of off-center to each other, and they made two clumps of nickel. So you had maybe a nickel distribution that looked like this in a collision of two white dwarfs. And again, you can convince yourself of what sort of line profile you get in this case, but you get sort of a double peak. So all of this is in a sense a ill-posed inverse problem in the sense that you can fit this. Since each wavelength is not telling you about one point in the atmosphere, it's telling you some integration over a plane, you can understand that there's more than one geometry that you can come up with that would give you the same fit to the observations. But you at least limit the possibilities that way. Okay. So you can get some sense of how things, these line profiles behave, as you say, increase the. This is a little animation showing as we increase the optical depth of the line. This Sobolev optical depth for some spherical geometry. The line gets deeper, the emission gets greater. So this is tau defined at the photosphere, and it's falling off as some power law from the photosphere in a radial way. Okay. And so the depth of the line is telling you something about the strength of the absorption, which you see never goes to zero even as the optical depth gets very large, because you still have some emission from those regions as well. And the minimum tends to move out as you get to very high optical depths for the reasons that we discussed, that for high optical depths you're actually occluding the photosphere even far away from the slice near the center. Okay? And as you increase the velocity scale, of course, naturally the lines are getting broader and broader. So for any line you see, you can basically infer something about the velocity dispersion in the ejecta. And then here's what I'm saying about the line source function. Depending on how much emission the line has, in LTE, this would be how hot the material in the atmosphere is relative to the photosphere. In non-LTE, you may have other effects. But basically, as you increase the source function, you can change from pure absorption to emission. Right? If the line emission is stronger than the photosphere emission everywhere in the atmosphere, then you never occlude the photosphere. You always get emission. And this may be something we see in interacting supernova, where we see pure emission lines, or in TDEs, where we see often pure emission lines. The line, even though there may be a photosphere material above it, the line source function may actually be greater than the intensity of the photosphere everywhere. And so you can measure that.
Usually in the supernova we'll have stratified depth, right?
Right.
Not all lines will have
Not all lines will have these profiles. Right. Yes. Right. Right. Well, it depends on the geometry, right? I mean, if I have a...
Oh, yes, not all elements, not all stresses because they're all in the separate layer.
Right, right. And so that's, again, yeah, you can do that exercise if I have, maybe if I can get this to go up one more time. I can get this up one more time. But you're right, yeah, if I have different layers, I may have, it may be similar to what I drew before, the thin shell case. I don't know if I erased it. If I just have material in some layer, some element is only in some thin layer detached from the photosphere, I might get mostly absorption. And then emission as well. So I encourage you to make this a practical use and to actually go through and well, not just have these pictorial ideas in your head, but also to calculate yourself spectral features and try to understand how we can use those to understand supernova mechanisms. How much time do I have left? Another 25 minutes. Okay. Other? Yeah, 20 minutes. Other questions? Yeah.
So then if you have Nico 56, downside is photosphere, outside the photosphere, or
Mhm.
maybe some mixing, so inhomogeneous. So,
Right.
so the line you're looking at maybe much more complicated future.
Right. So in this model, yeah, we've assumed that the emission is coming, from some centralized source. But you're right. If I had emission coming from some aspherical distribution here, I mean, maybe my nickel source is aspherical, or maybe it's off-center as well. I'd have to take that into account as well. I mean, I can do the same sort of game as long as I could define some surface of emission. And then, yeah, I would get different predictions as well. So you could generalize the model to that, as well as to other velocity distributions as well. So the other reason I wanted to kind of go through some of this transport stuff is to understand what happens in general for supernova light curves as well. So again, we've seen these analytic scalings that give us supernova light curve behavior, and they all depend upon the opacity, which is setting the time scale for radiation to diffuse out. But what really is giving us the opacity in supernova, here's an example. Now this is for solar metallicity, so hydrogen-rich material, showing you the different sources of opacity as a function of wavelength, right? So this would be appropriate for, say, a type 2 supernova. And you can see electron scattering, which is just a constant opacity. In this environment, since it's ionized, is dominating out here. This is the log-log scale, so this is, say, maybe above 3,000 or 4,000 angstroms. Electron scattering is a dominant opacity. So choosing a constant opacity in your light curve model of something around electron scattering may not be so bad. The other sources of opacity, like free-free, are subdominant. Bound-free, which is ionization from all these different elements in the mixture, can dominate in the UV. But then we have all these lines here that contribute as well. So what I've talked about so far is sort of imagined I had a continuum emitting photosphere and say a line above it. So maybe one of these strong lines that sit above the photosphere. But in type 1a supernova and in kilonova, and maybe for type 2 supernova in these bluer wavelengths, it's actually the lines themselves that are producing the opacity. It's this blend of many, many lines that themselves are weak, or they're so close together that they don't stand out as individual P Cygni profiles. They stand out as some sort of pseudo-continuum. Right? And that's what we want to estimate, and that's really going to get us to the heart of when I talk tomorrow about kilonova, why they are so different than other sorts of transients, right? And so the physics I described before is just as relevant here. If I have some, now let's say I have some opacity. Let's not think just about one line. Maybe I have lots of lines, right? That are populating my spectrum. And these lines here, of course, in solar metallicity are mostly due to iron because it's one of the most complicated elements we have in abundance in solar metallicity. So these are just a bunch of iron group elements. And so let's say I have all these lines sitting here. Well, let's say a photon starts trying to make its way out. And now we're kind of allowing ourselves to think about what's happening, inside this photosphere. The same physics applies that I just talked about. As the photon moves in space, it also moves proportionally in wavelength, and it'll move until it hits one of these lines. And again, that interaction will happen at a very small point in space. The photon may kind of hang out in this resonance region for a tiny bit of time, but then maybe it'll scatter off in some other direction. Again, the probability it scatters will just be 1 minus e to this minus tau so. All right. So it'll continue after it kind of maybe scatters its way through here. It'll continue on its way until it comes through. Maybe this line here, it'll come into resonance with at some point. maybe this one's too weak for it to scatter through, so maybe it just goes through unabated. Eventually it comes to some other line here that's optically thick, large syllabary of tau, and maybe it scatters again, so on and so forth. Scatters again, so on. Does this random walk. And the mean free path here is set by these lines as well, right? It doesn't matter, in a sense, how strong these lines are. What matters is if they are strong enough. That is, if their syllabary of optical depth is large, then they'll scatter the photon. But the mean free path the photon experiences is set not by the strength of the line, but the spacing in between, right? And so what matters, in a sense, is how many lines you have, not necessarily how strong the lines are. And so we can quantify that and calculate an opacity that'll be appropriate, say, for iron in type 1a supernova first, and then we'll do it for kilonova here. So the standard way to do this, and to estimate how optically thick some medium is that's dominated by lines, let's say this is some little piece of the spectrum here with some delta lambda, some bin I make. And let's say I have n strong lines on average per delta lambda. So I can choose this bin size however I want. Maybe it's an angstrom or something, a couple angstroms. And I can count the number of strong lines, which is, so we have optical depth greater than 1 or something. You could estimate that yourself. And so what's the representative opacity of that? Well, the mean free path here is sort of the distance traveled. And we already showed before, the distance traveled is just proportional to the wavelength shifted as well. So if the average spacing of the lines, let me write this. Write this over here. So the average spacing of the lines is say the bin size divided by the number of strong lines. What's that? Oh, we had a question over here? Yes, yes.
Here. So,
Go ahead.
sorry.
Yes, please.
So the y-axis here is the opacity.
Yeah.
Which is also proportional, I guess, to the density of the stone. So the more you have of the measurement, the more...
Yeah, so there's some subtlety here. I mean, this is the opacity, say, in a co-moving frame sense. That is, if I had some piece of gas at rest, the opacity would look like this. I'd have a bunch of narrow lines. But what the photons see is actually, as they move, of course, they're doing this Doppler shift. So the opacity they see is enhanced by the fact there is some velocity gradient that's moving them through these lines. So the relevant opacity that we're going to derive is not necessarily the one given by this. It's going to be an appropriate average of this that takes into account the Doppler shifting effects. So that's what we call an expansion opacity. So I guess I should say one could do a calculation including all of these lines here. But it's not so intuitive and it's hard to do numerically. So to try to understand the opacity that we want to put into, say, a simple light curve model, we want to, say, do an appropriate average of these lines, which I'll show you in a second. Well, I can write it this way. In general, we describe the mean free path of some material as 1 over the opacity times the density. And so maybe I should write this as an effective opacity or something. So the effective opacity is going to be related to the mean free path that the photon takes as it moves through here. And that mean free path is set by not the actual opacity, strength of these lines, but the spacing in between them. Right. So what I'm writing down here is sort of the mean free path, which is the distance traveled before an interaction with a line, is basically given by the spacing between the lines over the wavelength that we're at. So let's say this is this is some average wavelength that we're looking at. Times CT. So this is our same expression that we had before relating distance traveled to wavelength shifted. But here we're saying the wavelength shift between kind of the average distance between lines, average wavelength distance between lines. Right? Questions on that? So this is the mean free path, and so we can write the effective opacity as basically just rearranging this as 1 over density times the mean free path. And if this is the mean free path, our sort of effective opacity, or what's often called an expansion opacity, is basically 1 over rho this mean free 1 over this mean free path. Okay, which is sort of the wavelength we're at over the number of strong lines in a wavelength bin divided by CT. Okay. Yes.
So if you take supernova over the section of the place, how much does the capacity change? I mean, with light curve, it usually assume.
Right. Yeah. Yeah, it's a good question. So what you can kind of see here is the opacity is maybe less sensitive to density that you might expect. So as time goes on, the density of the expanding ejecta is going down. The strength of these lines may be going down. But like I said, it doesn't really matter the strength of the lines. What matters is how many strong lines you have. So as long as those strong lines remain strong, you're all right. So if I lowered the density here over time, maybe one or a few of these lines may drop below the criteria for strength, but most of them will remain strong. So the opacity does, in a sense, regulate itself to be not very dependent upon density in time for just this physics reason. We just want to count the number of strong lines. We don't care how strong they actually are. It may be more sensitive to temperature if I change the ionization state or something. As I get high and ionize everything and these lines go away, then I might have some dramatic difference in the lines. That's all a question. Yeah, so at some, in some regimes you may be ionized enough that the, say electron scattering maybe start dominating over these lines. If I ionize myself away, maybe all my lines, if I'm in a high ionization state, are more in the UV. And so the opacity of relevance may be electron scattering. But for type 1a supernova and for kilonova, which I'm moving towards, the lines tend to always dominate, or usually always dominate over electron scattering.
What is the
And so this.
number for lambda times n divided by delta lambda?
Yeah, so this you need to calculate. So this is the number of strong lines. Actually, this is often written instead of just a number count. We can do it a little bit more cleverly as a as sort of a sum over 1 minus eta minus tau Sobolev, which will count both the weak and the strong lines. And so the number here that you get is really the density of lines will depend quite sensitively on the material that you're talking about. So for, say, hydrogen or something, a very simple atom, there's not many lines at all. This opacity is quite small. Electron scattering will dominate. But for iron, the number of lines can be large, especially the line density gets high at short wavelengths. And so this number gets large. And so we can do, if I have time, I don't know how much time I have left, we can do some counting of different elements to estimate what that number is and understand why the opacities are different. But any other questions before? Yeah, Udi.
One thing I never understood. Usually the opacity for quoted function of the composition. So people say I have iron line dominant opacity roughly 0.1.
Right.
Saying nothing about what is the velocity gradient in the outflow, for example. Is it the same for 10,000 or 100,000?
Right.
I can inject that. So
Right.
I look at this calculation of this what I saw before, and I don't see why should it be depending on the composition only. Why should be one number per composition?
Well, you can see here it has no dependence upon the velocity scale, right? Since that, I mean, it has some dependence on time, but it's really an issue of number counting, right?
Yeah, but if I take the same amount of material
Uh-huh.
and I let it, I just increase the velocity by a factor of 10, for example.
Right.
Now I want the photon to cross this detector.
Right.
Then if the velocity is larger by a factor of 10, so it's the range of Doppler factors.
Right.
So I'm crossing more lines basically. But it's hitting rho over there. Okay. Rho is changing.
Well, I'm still crossing the same number of lines. You know, the spacing of the lines here, this is looking at the opacity in some, say, little parcel of gas. The spacing of the lines doesn't depend upon, you know, the velocity or anything. And what matters is sort of the distance you go between these lines, which is independent of the velocity of that eject as we should, right?
Kappa is per unit of mass.
Kappa is per unit of mass, yeah. So there is a 1 over rho here if you're talking about kappa.
Yeah. So
And
just
so,
taking a typical
yeah,
rho,
yeah.
This is how you get this typical opacity.
Right. So so this number, yeah. So there is some scale. If you're looking at it in terms of kappa, there's a 1 over rho here. If you're looking at it in terms of, say, an extinction coefficient or just a mean free path, it doesn't depend upon
So
that.
usually when people quote a number, it's for a typical rho.
Yeah. So if you change rho but keep these quantities the same, you're right. Yeah, it has some somewhat counterintuitive behavior. As you go to lower densities, this number goes up. I think that's true. Yeah. I'm probably missing CT when I dropped it here, yeah. Okay. Maybe I should stop here and pick up next time with describing how this works for different materials, different elements in type 1As and in kilonova, and then talk about the kilonova light curves and observations and so on and so forth. So any last questions? Yes?
Is there a way you could use observed spectrum of the supernova to calculate this opacity for using the light curve, for example?
That's, yeah, I think that's tricky. I mean, this opacity we're talking about here is sort of this blend of all these many lines. It's hard to pull that out of the spectrum itself in the analysis when you have many lines blended together. With individual lines, you can, as we talked about, you can infer their optical depth and their velocity distribution and all that. But for the blend, it's a little bit tough. So I'm not sure there's an easy way to pull it out. Yeah, that's a good question.
Then how this your temperature here is 10 to 12.
Right.
Remember, you like a double or what 10 times more or decrease a factor of 2. How this plot will change?
So what will mostly change, yeah, if I change the temperature here, what changes primarily, well, there'll be a few things that change. The ionization state may change if I go to low. So this will be, hydrogen's ionized and iron group is ionized to some degree. If I go to low temperature, say, 5,000 Kelvin, hydrogen recombines, so this electron scattering will go way down. And these iron lines will probably change as well. We saw the optical depth was, proportional to some Boltzmann factor, so we may get weaker temperatures. So in general, as you go to a low temperature where things start to get neutral and not excited, the opacity will tend to drop sharply. That happens for hydrogen, of course, once you reach the hydrogen recombination temperature, but it happens for other elements too when they tend to recombine to neutral. And so we may actually see evidence of that in kilonova as well, just as in type 2p supernova, we see sort of a special temperature which things regulate to when hydrogen recombines. I'll show in kilonova there may be a special temperature where the heavy elements recombine and regulate the temperature as well.
Questions?
Good. Oh, one more. Uh-huh. Yeah. So we've we've seen that. Yeah. So you have the tools. I hope to start doing more quantitative analysis rather than just measuring a single velocity. You could, actually measure strength of lines for different. You can actually calculate a line profile and see where it is. But yeah, what we've seen is for optically thick lines, the point of minimum tends to move out because you get absorption to longer and longer radii. And if you play with this code, you'll get some intuition into how that happens. And so, yeah, this region is sort of telling you where you have sort of the highest optical depth along that plane that's going to absorb things. And if that happens to be near the photosphere, you'll measure the photospheric velocity, but there's no guarantee it'll be near the photosphere. And so you may be off by some, it's hard to quantify, but depends on how optically thick that line can be. Yeah.
I'm surprised that the shape is still changing even though tau is already huge.
Tau is huge, although it is, this is the value at the photosphere, and in this calculation it's sort of falling off as some power law away from it. I forget how steep it. I forget how steep it was, but in the limit that it's optically thick everywhere, the minimum would happen at sort of the outermost or near the outermost velocity. So you get an even. If I increase this even further, this edge would get sharper and sharper, and this minimum would move to sort of the outer edge of my ejecta. Right? Okay.
So still, what is this number, let's say, for ion lines without the CP?
Oh, the number of lines per wave. No, there are strong lines per wavelength bin. We could back it out. I'd have to think about that. Yeah. Well, the number Udi's quoting of saying this effective opacity is something like 0.1 will give you some suggestive number of what that what that line density is. I forget off the top of my head, but the main thing is how it scales with different sorts of atoms. Different sorts of atoms will have higher line densities than others. Yeah.
Is it possibly that these were dominated by the weak lines, many weak lines, there are these strong lines? The 1 minus tau, tau, and then density drops off. So it's independent.
Yeah, at some limit that will happen as you get to many weak lines, right? So there are some, yeah, right. If I expand this for small tau, yeah, then the density distribution cancels out. So in general, it's the strong lines that are sort of the number density of the strong lines that are dominating. But as you get later and later, and the optical depth of most lines drop, you might reach that limit. Okay. Wow.
What do you want to do then half an hour from now?
Thank you.